Okay, so the cardioid gets its name because it looks like a heart, and it's one of these really beautiful classic polar curves. So when we're plotting stuff in polar coordinates, I'm just going to think a little bit about what some of the values are here for different thetas. So if theta is 0, we're talking about 1 plus the sine of 0, so that's 1. So it's like here. So there's the point 1 comma theta. Remember, that's the weird thing about polar coordinates is even though we think of our inputs are thetas, then when we write the points out, we tend to write the r first. Distance first, then rotation. If I put in pi over 6, I'm getting 1 plus a half, which is 3 halves. So I end up here. And then at pi over 4, we've got 1 plus root 2 over 2. So that's further out. And then pi over 3, we've got 1 plus root 3 over 2, because everyone loves the unit circle. And then at pi over 2, that's when the cardioid takes its biggest value, because we're going to get 1 plus 1, or 2. And so we sort of rotate out to here. So we've made a shape kind of like this. It's actually got a horizontal tangent up there, if I had drawn it properly. Once we start looking at the negative angles that are sort of the negative second quadrant angles, we know that sine values are still they're gonna have symmetry with what happens in the first quadrant. The sine values still stay positive, so my art's gonna be moderately egregious here because it's hard to mimic it perfectly, but we'll come in like this, 5 pi over 6, and then all the way down to being at 1 there. So at this point, if you think about what's happening here at pi, we're just getting 1 because it's 1 plus the sine of pi, which is 0. So there we are. So then what's cool is what happens once we move beyond that point. Notice this curve always has positive values or values greater than 0, but then they get tinier because now we're going to have negative sine values and they start cutting some out of the curve. So it kind of does this, which is really cute. And one of the fun games to play is to find those horizontal tangents. It's a good that's a good thing. So where are those horizontal tangents happening? It's not an easy question. But that's the cardioid. It gets its name because of its cute little shape, kind of like, I always think it looks like a butt, but that's just me. How do we draw tangent lines to these? And then we can relate that. The graph here that I drew is an example of a Lima sun, which is named after a mathematician of the same name. And when we want to draw a tangent line to a polar curve, what we have to be careful about is the fact that polar coordinates r is a function of theta, but then we can consider both x and y to be functions of theta themselves. So we have this relationship where if we want to find the slope of the tangent line, we really need a dy dx again. In order to get that dy dx, these are the parametrized equations that we're using in both cases. So differentiating by the product rule, dx d theta would be derivative of the r, so f prime of theta times cosine, minus f of theta times sine, because the derivative of cosine is negative sine. dy d theta then is f prime of theta times sine theta plus f of theta times the derivative of sine, which is cosine. So if we look at what dy dx is, dy dx is this hideous quotient, which on the one hand you could just use like this. F prime of theta, or what typically, like the way you'll often see it written is just as dr d theta sine plus r times cosine, and then dr d theta cosine minus r times sine. Usually we just have to use it like this. So this is one where I don't recommend memorizing it. You just remember that you have to convert to parametric and then take the slope of the tangent line. But I have seen situations where you could kind of make it cleaner, or do it in terms of x and y if you want. I mean, because r cos theta is just x, so in some sense this is dr d theta sine theta plus x over dr d theta cos theta minus y, but that's not a convenient way to think about it because now we've got an equation that's in terms of theta and r all at the same time. But this can help sort of morally to kind of keep that in mind. So if we went back to the cardioid and we wanted to find the horizontal tangents, then if we're looking for dy dx, what is that in this case?
So here's the formula on the bottom left for the slope of the tangent line to a polar curve. And on the top right, you can see where I've gone through the math. The derivative of r with respect to theta here is cosine theta. Then I've input that expression into my slope of the tangent line formula. And in that next line, I just expand it out. So 1 plus sine theta times cos theta on the top, and 1 plus sine theta times sine theta on the bottom. Now let's simplify.
In the numerator, you have 2 cos theta sine theta plus cos theta. And in the denominator, you have cos squared minus sine squared minus sine.
So if the question we're asking is horizontal tangents, I need to set dy dx equal to 0. Now I know that in order to do such a computation, I'm looking at the numerator. So I have this 2 times cosine theta sine theta plus cosine theta equals 0. And so I'm going to factor out a cosine of theta, and I get cosine theta times 2 sine theta plus 1 equals 0. So that means that I'm going to have either cosine theta or 2 sine theta plus 1 could equal 0. So cosine theta equals 0. That occurs when theta is pi over 2, or it can also occur when theta is 3 pi over 2. However, you can notice that the 3 pi over 2 case is corresponding to a different radius, so that the denominator 0 as well and cause other problems. Really, the one we're looking at, this horizontal tangent line, this is happening when theta is pi over 2. And then for the second one, we're looking for solutions to 2 sine theta plus 1 equals 0. So that means we're solving for when sine theta equals negative 1/2. That's the other solution. And that occurs when theta is 7 pi over 6 or 11 pi over 6. My art here's a little off. You can see I didn't quite have the horizontal tangents right in the right place based on my artwork.